Hi, my name is Priyank Agrawal. I'm a master's student in computer science at University of Illinois. Today I'm going to talk about my joint work with Theja Tulabandula titled Learning by Repetition, Stochastic Multi-Arm Bandits under Priming Effect. Let me introduce the key term here. Priming effect refers to the induced behavior changes due to repeated exposure to some stimuli. It comes in two flavors, wearing in and wear out, which I'll introduce in a while. In terms of online learning, this leads to a situation where the current rewards depend upon the past action choices by the learning algorithm. In this work, we model the priming effect with the help of stochastic multi-arm bandits. We analyze and calculate regret upper bounds and also talk briefly about the lower bounds. Such a framework has many applications. For example, in commercial systems and e-commerce product placement, the learner is the online platform, and it has the problem, or it needs to solve the problem where it needs to present a particular product or a set of product to the consumer out of multiple possible choices. The number of times a particular product is chosen affects the consumer behavior. Similarly, in online advertising and multi-domain advertising, the number of times a particular ad is shown for a particular product affects the user behavior and response towards that product, which directly affects the consumer firm revenue. To motivate it further, consider the example of online and multi-domain advertising. A firm may decide to show a particular ad number of times to the consumer, or it might show the different types of ads for the same product to the consumer. This might lead to wearing in, where the consumer starts responding to the ad only after they have seen the ad multiple times and hence generate revenue for the firm, or wear out, where the consumer becomes unresponsive to the particular ad because they have seen it too many times. The online learning problem here is the rewards get accrued when the action has been played enough number of times in the recent past. However, the rewards stop accruing when the action has been played too many times in the recent past. Let's see how the interaction model goes in this case. The online platform of the learner wants to learn the efficacy of key advertisements or action. Each action is associated with a stationary reward distribution with unknown mean. At round T, the learner chooses one particular action. The environment samples generate samples from three different distributions: RTJ from the reward distribution, D and Z from the where in parameter distribution and where out parameter distribution, respectively. The learner does not see the reward RTJ directly, however, it observes XTJ, which can be thought of a mutated version of RTJ when passed through a history function. Specifically, XTJ is RTJ multiplied by an indicator function where where the priming parameters, that is D and Z, act as barriers in the indicator function. Specifically, in the wherein case, the D is the lower limit, and in the case where both where in and where out effects are active, D and Z form the lower and upper limit to the indicator function respectively. The history function ftj of n encapsulates the contribution of prior interaction in the past n rounds. It is non-decreasing in n and assumed to be dependent only on the number of times armj was played in the recent past. As a modeling assumption, we choose it to be number of times armj was played in the most recent n rounds. This implies at a given time round, the environment will generate sample dtj and ztj. If the number of times armj was chosen lies between these two numbers, the learner will accrue reward, or else it will not. The learner knows the past history, length, expectation of D and Z, and the time horizon. Our results are as shown. Notice that the leading term is sublinear in time, and it matches the lower bound of stochastic multi-arm bandit without any priming effect up to logarithmic terms. The priming effects are only additive and vary graciously with the parameter expectation of t. In case of wear in, wear out, the dependence on expectation of z is implicitly captured. As you can notice, there is a potential gap of root k in the wear in, wear out case. Let's look at the main idea. We need to control the number of arm plays in the recent and length history. What if what if we play an arm repeatedly multiple times? In that case, the first few rounds and the last few rounds will not accrue reward due to wear in and wear out effect respectively, and only the rewards will be accrued in the middle portion. The length of these segments is stochastic and history dependent. Building on this idea comes to a large number of phases wherein a specific arm is played repeatedly, where the duration of each phase comes from some analysis. We can segment, we can divide these segments into regions of wear in effect, wear out effect, and the portion where it accrue reward. For each arm, we show that across multiple phases, the regions can be graded as independent martingale difference sequences. Using the standard martingale concentration results, we can have a control on the estimated reward, mean reward of the arms as a function of phases in each arm is played. This leads up to the learning strategy. A primary learning framework proceeds in phases. So for each phase M, the algorithm loops over all the active arms and play each of the active arm CM times. And at the end of the phase, the algorithm deletes the arms which are delta M away from the best estimate. CM is determined by the concentration properties of the martingale differences sequences, and delta M decreases exponentially with each phase. To conclude, we model simultaneous wear and wear out effect. We extend the phase-based UCB2 strategy. Future directions include working with richer history functions, learning with unknown expectation of D, Z, or capital N with C is history length. My name is Priyank Agrawal. Feel free to reach out to me if you have any questions about this work. And I will also be seeking PhD positions for fall 2021 in the areas of online learning and reinforcement learning theory.